Welcome to the sixth video in Introduction to Quantum Field Theory. Let me just make sure, yeah, my AirPods are connected. So we'll be talking about field dynamics. This is a purely uh, visualization focused episode. We are not going to talk about the math, really. We're just going to look at visualizations. We are used to talking about how things evolve in time. That is, we treat time and space separately. We know this is wrong due to special relativity. Time is a dimension, like space is. So while we think about the evolution of a field in time, it is important to remind ourselves that these fields are actually static in space-time. To gain an intuition for field dynamics, we will imagine that scalar fields are like matrices. So I can draw a scalar field. For example, I'll use blue. Okay, my hand covers that part, so I need to draw from the other direction. So we can imagine this as a scalar field, or this is a scalar field. But then to imagine how it behaves, we will imagine this as a matrix of sorts. So scalar field equivalent to, say we have a mass here. Actually, what I'm going to do is draw a circle, fill it in, and just copy this circle so we can imagine field almost like bugging me like this. And we can imagine there are these connections. I'll do it with black. There are these connections between each little dot, and these are attached to springs. So we can imagine scalar fields like springs, springboards, or matrices. So what these are, we're going to start zooming in and focusing on them. So take a look at this. This right here is an individual harmonic oscillator. And it evolves in time as what I'm about to write. So we have some kind of equilibrium position. Okay, we have this. Well, let's say something starts below equilibrium. Then it can go like this, up to equilibrium, over equilibrium, back down to equilibrium, down again, back up to equilibrium. And we can say that these are just mass springs, or this is a mass spring evolving in time. So we can say that this is your initial time. This is T1, T2, T3, T4, T5. So an individual little ball in this mattress will oscillate up and down. So if it's pressed, you can imagine it pressed down, then it has some energy, and so over time it's going to go up and down and oscillate. But how would this work for something like this? Because if you imagine that there are bunches of springs all together, and they all oscillate on their own, they're not going to affect their neighbors. So you end up having to factor in this right here. It's far from a circle. So this, let's bring it down here. This is what's called coupled. These are coupled oscillators. So we'll consider the system first at some time t, and we can say that the system has some kind of initial discrepancy from equilibrium. So that each oscillator is coupled to the one immediately next to it. And if we suppose that this kind of excitation where the oscillators are a little higher relative to the oscillators around them, we say that this has kind of a linear momentum of sorts, then as this evolves in time, so we can go to T1, we can take this. Oh, come on, I cannot. There we, there we go. So it can move as so. And then you can imagine that that this can just keep going on. So the excitation here is pulled down because its neighbor is down. So it returns to equilibrium, and this one stays up, or then this one eventually pulls this one up. So, and then that keeps going. So this pulls this up. So it goes this way, this gets pulled that way, and that gets pulled down. And it keeps going up, pulled down until it's like this, up, pulled down. These are both up. So it's an excitation traveling through a field of coupled, or a mattress of coupled oscillators. Then if we say that n equals let's do this, n equals the number of oscillators, then as the limit, or rather, as n goes to infinity, the or as n goes to infinity and the separation, so if we can say that, and the separation between oscillators lessens. So as the separation becomes smaller and the number of oscillators goes up, we get a continuous field. So the way to picture this is, let's then take third one, or take these. So say we have 3 coupled oscillators. Then we can double things. Go to here. We can have some here. So you can see that there are now more oscillators and the space between them is smaller. And you can do that again. Don't want to convert that. Want to copy it. And if we double it again, keep going. And you can kind of skip ahead to get the idea. But now I'm just interested in seeing. Now I'm just having it see how much I can do. Yeah, okay, no, it's so if we continue all the way up to infinity, then what we effectively get is this black continuous thing. Then you can kind of imagine all the springs are below. And we can now consider the equivalent of this system. Now consider the equivalent of that system here. So there can be some kind of initial oscillation, or excitation rather. And if it has this kind of momentum, then it's going to eventually just look, it's going to move like this. So as fields, or as these matrices become more and more dense and more coupled, then as you go take that limit to infinity, then it just becomes a continuous solid field. and the dynamics are the same as if they were just coupled oscillators. So you can imagine a field like this, just like a set or a mattress of springs.